It always starts with the best of intentions.
Oh, always.
Have you ever been sitting at your keyboard just staring at a massive code base and you make what you think is a simple, elegant one-liner code change?
The famous last words of software engineering right there.
Right. You tell yourself, this is brilliant, it's efficient, I'm going to commit this, grab my coffee, and I'll be completely done in like 5 minutes.
And then reality hits.
Exactly. You push the code, and then you just find yourself spiraling into this 3-hour debugging abyss, basically questioning every life choice that led you to this exact moment.
It really is a universal rite of passage. You experience that sudden, very specific drop in your stomach when the build fails.
Oh, I know that drop.
Yeah, and the error message makes absolutely zero logical sense, especially based on the tiny change you just made.
Well, that feeling is exactly where we are heading today. Welcome to the deep dive.
Glad to be here.
Our mission today is to unpack this really fascinating, highly detailed postmortem by a developer who goes by the handle at LUK036.
Yeah, they documented an epic battle.
They really did. It was a battle with a CMake target conflict using CPM, which is the C++ package manager, for anyone not familiar.
Right.
And we aren't just talking about breaking, one isolated side project. This developer applied a tiny optimization across more than 35 different C++ projects in their GitHub organization.
Which is, applying a global sweeping change to 35 distinct code bases is just a massive roll of the dice.
Yeah, it's huge.
It's kind of similar to a doctor prescribing the exact same medication to, say, 35 different patients without checking any of their individual medical histories.
That's a great way to put it.
You're assuming this uniform biology in a system that is inherently, very diverse.
Okay, let's unpack this, because on the surface, the optimization seemed incredibly smart.
Sure.
It was this one-liner pattern, basically. Try to use find package first, and if that doesn't work, fall back to CPM.
Right, fallback strategy.
Exactly. And for anyone not living in C++ every day, this basically means asking the system, hey, do you already have this package installed locally? If yes, use it.
And if no, let the package manager download it.
Yeah, it was supposed to be this best of both worlds scenario. And for the simple projects, the ones that only needed direct dependencies like FMT and Spoidlog, it worked perfectly.
The initial data certainly validated their assumption. The continuous integration pipelines, the CI workflows, they were just humming along.
Everything was green.
Right, 4 out of 5 workflows passed with flying colors across multiple operating systems. And, when you see that much green on your dashboard, you assume you secured a total victory.
Until that fifth workflow.
Ah, yes, the install workflow.
The install workflow completely exploded, and it exploded in a really weird place. The error was firing at line 309 of FMT's very own CMake lists.txt file.
Which is deep in there.
Right. Basically, someone or something was calling CPM add package for FMT a second time. The system was trying to pour the exact same concrete foundation twice in the exact same spot.
And to understand why that foundation cracked, we have to draw a hard line between direct dependencies and transitive dependencies.
Okay, lay it out for us.
Well, this isn't just a quirk of C++ing, right? It's a fundamental lesson in how complex, layered systems interact behind the scenes.
Yeah.
Often in ways we can't easily see at the top level.
I was trying to visualize this layered interaction, and I keep thinking about it like a party guest list.
Okay, I like where this is going.
So let's say you're hosting a gathering. A simple project is like you directly inviting your good friend FMT to the party. You put their name on the VIP list, they show up, walk through the door, everything is great.
Makes sense.
But a complex project is like you inviting your friend LLGO. Now, LLGO is the kind of guest who brings their own friends.
And plus ones?
Exactly, the plus ones. They bring FMT as their plus one. But LLGO doesn't realize you already invited FMT personally.
Oh, I see.
So now FMT is trying to walk through the front door a second time, and the bouncer, in this case CMake, is absolutely losing its mind trying to figure out how one person can check in twice.
What's fascinating here is that your analogy perfectly captures the structural flaw in the developer's dependency web.
Really?
Yeah, because the simple projects, they only had direct dependencies. So find package runs, it finds FMT, the CPM fallback is entirely bypassed, and the CI passes.
Right.
The failure only triggered when those transitive dependencies, the plus ones like LAlgo, were introduced into the environment.
Because LAlgo was managing its own dependencies internally using CPM.
Precisely. LAlgo contains its own internal command saying, I require FMT, so let me use CPM to fetch it.
Ah, okay.
So your very first command, find package, already brought FMT into the global build. Then, down to the sublayers, LLGO wakes up and tells CPM to add FMT all over again.
Which sets up the central mystery of this entire postmortem. Why couldn't the package manager simply look at the guest list, see that FMT was already safely inside the party, and just move on?
That is the million-dollar question.
And since the package manager couldn't figure that out, the developer went into pure reaction mode.
Panic mode, really.
Yeah, once that install workflow crashed, they entered what I'm calling the cycle of despair.
That's a very accurate name for it.
They spent 3 hours trying to fix this, mostly by guessing instead of actually understanding the underlying mechanics. Let's walk through this gauntlet, starting with their first instinct, which was tweaking the environment.
What do they try first?
They just pulled their new optimization script, the specific .cmake file, out of the test configuration entirely.
A logical retreat, honestly.
Yeah.
If the new code broke it, just remove the new code.
Right, but doing that completely shattered LLGO's installed configuration. It failed on something called CPM.cmake prefix path, which is essentially the treasure map for the compiler, right?
That's a great way to put it. The CMake prefix path tells the system exactly which directories to search to find the libraries it needs.
Okay.
By ripping out the optimization script, the transitive dependency suddenly lost its map.
Oh, well.
Yeah, it didn't know where to look for its required packages across the different project environments, which resulted in a fatal pathing failure.
So retreating didn't work. Since that failed, they swung to the opposite extreme. Brute force.
Always a risky move.
They tried using a built-in feature called CMakeable find package. They basically slapped a giant do not enter sign on the door, forbidding FMT from loading at all.
And this reveals a really fascinating quirk about how build systems handle conflicting instructions.
It worked for one simple project, Core Solver TruePPR, because that project didn't have any deep, complex downstream dependencies.
Right.
But it instantly failed on another project called Multiplierless 3P. Down in the basement of that project's code, a script was looking for FMT and declaring it as a required dependency.
That is the classic unstoppable force meeting the immovable object.
Totally.
You cannot globally disable a package at the top level if another part of the system is explicitly coded to declare it as strictly required down at a lower level.
It's just break.
Yeah, CMake treats the required keyword as a blood oath. If it can't fulfill it, the engine simply halts and throws a fatal error rather than risk building a broken application.
Okay, so brute force is off the table. Then the developer tried to trick the system's logic.
How so?
They set a variable called CPM.fmam to yes. The assumption here is pretty obvious. They thought CPM would read this variable, see the word AD, and smartly skip installing it.
I see the logic there.
But the system completely ignored it. And I have to admit, I have some serious questions about this one. Wait, setting a variable that literally says FMT is added didn't work.
Nope.
Why wouldn't a package manager listen to its own naming conventions? If I set a flag that literally says it's added, shouldn't the tool respect that?
It absolutely should if the tool was actually programmed to read that specific flag.
Oh.
But this highlights the danger of relying on assumption about how a tool should be built, rather than checking how it actually operates. The developer was using CPM version 0.32.0. If they had paused and just opened the source code for that specific version, they would have seen that the tool simply doesn't check a loose variable called ADD.
Then what is it actually looking at if it doesn't check the variable?
It checks a highly specific internal array, a list called CPM packages.
Okay.
CPM literally runs a localized command to see if the package name exists inside that exact list. You can shout CPM FMDAD into the void all day long, but if the tool isn't hard-coded to listen for that specific phrase, it's going to completely ignore you.
Oh, that is painful.
Very.
If you are listening to this and wondering why on earth they didn't just read the manual or the source code first, you are not alone.
No, we've all been there.
But in the heat of a failing CI pipeline, panic totally overrides logic. So they try another trick. They create an interface stub target for FMT.
Which is an attempt to create a decoy.
Exactly. It's like putting a cardboard cutout of a person at your party and hoping the bouncer thinks it's a real guest.
I love that.
It's this hollow shell that says, I am the FMT package, but contains absolutely no actual code.
Right, just an empty shell.
And the illusion might work from a distance, but the moment another package, in this case, Speedlog, actually tried to interact with FMT and compile its internal libraries, it crashed headfirst into the cardboard cutout.
Because Laserlog needs tangible, compiled binaries to link against. It can't use an empty interface.
Yeah.
It recognized the target name, Tried to extract the underlying data, found absolutely nothing, and just crashed.
So the cardboard cutout fails. Finally, the developer opens the source code.
At last.
They see the CPM packages list you just mentioned, and they try to manually inject FMT directly into that internal list. But even this fails.
Of course it does.
Yeah, it fails due to scope boundaries with a command called fetch content. No, wait, what do you mean by scope boundaries? Is fetch content basically creating a walled garden for the code?
Kind of, yeah.
If I'm using a package manager, shouldn't his whole job be to manage things globally across the entire project? Why would a modern tool isolate dependencies in a basement where the rest of the house can't see them?
That is a brilliant question, and it really cuts to the heart of CMake's historical design.
Okay.
See, CMake wasn't originally designed as a modern package manager. It's a build system generator.
Right.
So to prevent massive, messy projects from tripping over their own feet, CMake isolates variables within the subdirectories where they are created.
For safety.
Exactly. Fetch content operates inside one of these localized scopes. So the developer updated the list in one room of the house, but CMake's architecture intentionally prevented that update from propagating to the other rooms.
Oh, man.
It's a safety feature that ironically becomes a massive trap when you actually need a global state.
5 failed attempts, 3 hours of sheer debugging fatigue, all driven by guessing rather than reading.
It's exhausting just hearing about it.
But having exhausted every possible trick, the developer finally digs into the actual molecular level CMake mechanics. And here's where it gets really interesting. This brings us to the core technical revelation of this deep dive, the great CMake wall.
Yes. This is the moment we stop looking at the symptoms, the failing paths and the ignored variables, and finally diagnose the underlying disease.
Diagnosing that disease means looking at the label CMake is attaching to these files. It turns out CMake has 2 distinct ways to classify these targets.
Right.
When the developer's original script ran find package first, CMake created a target for FMT, but it classified it as an imported target.
Correct.
Later, when the transitive dependency woke up and triggered CPM, CPM tried to create its own target for FMT, but it tried to create it as an alias target. And those 2 classifications violently conflict.
They are fundamentally incompatible in the CMake ecosystem.
How so?
An imported target represents a library that was built completely outside of your current project. It's an external black box. An alias target, on the other hand, is strictly a pointer to something built inside your project.
I was trying to wrap my head around this, and it feels like a massive conflict of physical and digital realities.
Go on.
An alias is like creating a shortcut on your desktop. It's just a pointer to a file that already exists on your machine. But an imported target is like plugging in a physical external hard drive.
Yes.
You can't create a desktop shortcut named FMT if a physical folder named FMT is already sitting in that exact same directory.
Exactly.
The operating system panics because you're telling it this is an internal pointer and this is an external physical object at the exact same time.
That is the perfect way to conceptualize the conflict. CMake's internal target registry simply cannot allow an internal shortcut and an external black box to share the exact same system ID.
It just can't handle it.
No,
Yo.
the rigidity of that registry is what caused the crash. But that raises the million-dollar question. If the registry already had the external hard drive plugged in, why did CPM try to create a shortcut for it in the first place?
Yeah, why did CPM have this massive blind spot? Why didn't it see the imported target that was already sitting right there on the desk?
Because of namespaces.
Those spaces.
Yeah. When you look at CPM's internal code, it explicitly runs a text check that looks like this. If target FMT.
Okay.
It is looking for a bare target, a simple string of text with no special characters.
Yeah.
Just the letters, FMT.
But find package doesn't use bare text, does
No,
it?
it doesn't. When find package ran earlier, it created a namespace target. It created FMT : FMT
Wait, what?
with 2 colons in the middle.
Oh, wow. 2 colons.
2 colons. So CPM walks up, looks at the registry and says, hey, do I see a target named FMT?
And the registry says, no, I only have FMT.FMT.
Exactly. The registry says no.
Yeah.
So CTM says, great, it's not here. I will download it and install it myself.
Oh my gosh.
It downloads the package again, attempts to register it as an alias, and triggers the fatal collision with the existing imported target.
That is insane.
It exposes a massive gap in our abstraction layers. We trust these powerful package managers to handle complex topological nuances, but under the hood, they're often just running rigid, highly literal text checks.
That is wild. A 3-hour organization-wide debugging nightmare caused by two colons.
Two little colons.
So, armed with the technical why, the developer desperately needed a practical how. How do you actually fix this across 35 projects without breaking anything else? And this brings us to attempt 6, the breakthrough.
The moment they finally stopped guessing and started engineering.
They stopped throwing fixes at the broken projects, and they finally looked at a project in their organization that hadn't broken.
Ah, smart.
Yeah, a reference project called ProjGeom. Its test installation workflow had been passing perfectly from day one.
When you are completely lost in a complex system, finding a working baseline is often your only lifeline out of the maze.
Yeah, absolutely.
Comparing a broken state to a known working state is a fundamental engineering principle. So, what was ProjGeom doing differently?
It turns out ProjGeom didn't use that global one-liner optimization script at all. It didn't use specific.cmake.
Interesting.
Instead of trying to use a clever fallback pattern, it just found every dependency individually. More importantly, its dependencies, things like FMT, CD log, and fractions, had absolutely no transitive CPM chains.
Okay, so a simpler structure.
Yeah, there was no algo hiding in the background trying to retrigger the package manager. It was a completely flat dependency structure.
And seeing that contrast between a flat structure and a deeply nested structure is what led them to the real solution.
Yes, they realized they couldn't treat all 35 projects as identical clones. For the simple projects like AllGen CPP and AllDCPP, the original optimization script was totally fine. It was highly efficient.
Right, because there were no plus ones.
Exactly. But for the complex projects, the ones with deep transitive chains like core solver TIP-PEP and multiplier list TEP, they had to abandon the clever optimization. They had to use CPM add to package consistently across the entire chain.
They had to respect the distinct topological shape of each individual project's dependency graph.
And they distilled this into a golden rule for their entire organization.
Oh, yes.
If project A depends on B and B manages FMT, you must use CPM add package for B. You let the package manager handle the deduplication internally.
Right.
But if project A only depends directly on FMT, with no middlemen bringing plus ones to the party, then you use find package.
It's about choosing the right tool for the specific architecture in front of you rather than, forcing a universal standard.
The result speaks for itself. They applied this golden rule, and all 6 previously failing CI runs turned green.
Everything compiled.
Everything compiled, everything installed. Ubuntu, macOS, Windows, all completely green. The 3-hour nightmare was over.
Finally.
So what does this all mean? We've gone from a deceptively simple optimization script to crashing the system with 2 colons and finally to a working pipeline. How do we synthesize all of this?
If we pull back and look at the macro level takeaways, there are 2 glaring lessons here.
Okay, let's hear them.
The first is about the allocation of time and the profound danger of assumptions.
Right.
20 minutes of reading the CPM source code would have definitively saved 2 solid hours of guessing.
It's so true.
We routinely treat our tools as black boxes, assuming their internal logic matches our human common sense assuming a variable named ADD actually adds something.
Right, which seems logical to us.
But in software engineering, the truth is only ever found in the source code. Read the code before you start guessing.
It's so tempting to just try one more quick fix, but you have to break that cycle.
You do. And the second takeaway is about the danger of false uniformity.
Okay, unpack that.
The developer's fatal flaw at the very beginning was treating 35 disparate projects as identical entities. They applied a global patch without checking the unique dependency DNA of each codebase.
Oh, yeah.
In complex systems, context is everything. A brilliant, highly efficient optimization in a simple environment becomes a destructive force in a highly networked, transitive environment.
It really is a cautionary tale about the seduction of the one-size-fits-all solution. It just doesn't exist when deep dependency chains are involved.
It rarely exists anywhere in complex engineering, honestly.
So as we wrap up this deep dive into the trenches of CMake and C++ package management, the value for you listening right now is incredibly practical.
Very much so.
The next time you find yourself stuck on a bizarre, inexplicable bug and you can feel that debugging fatigue setting in,
And you will?
you definitely will. When that happens, take a breath. Stop throwing random fixes at the wall. Stop creating cardboard cutouts hoping to trip the compiler.
Step back and map the system.
Yes, map your dependencies. Find a working reference point, a baseline that you know functions correctly. And most importantly, open up the hood and read the actual source code of the tools you are relying on. Don't let yourself fall into the 3-hour abyss when a 20-minute read could point you straight to the exit.
It really highlights a paradox in modern development that we all need to confront. Think about the tools you use today. NPM, pip, cargo, CMake. You probably ran a dozen commands that seamlessly downloaded millions of lines of code.
Yeah, without even thinking about it.
We rely so heavily on these sophisticated tools to abstract away all the tedious complexity of our jobs.
Right.
But when those abstractions leak, like CPM's inability to see a namespace target just because of two colons,
Mhm.
our absolute reliance on that magic suddenly becomes our greatest vulnerability.
Oh, yeah.
How much of your daily sanity is hanging by a thread on a fragile text check you've never actually seen, just waiting for two colons to bring the whole thing down?